welcome back to my channel. Today in this video, we're going to be interviewing one of the brightest minds on the planet, Professor Jim Gates, who is a pioneer in supergravity and supersymmetry. He also earned the National Medal of Science, and he was also part of the President's Council of Advisors on Science and Technology, also known as PCAST. He also holds the Clark Leadership Chair at the University of Maryland, and he also teaches in the Department of Math and Physics. He has also written 200 papers in this field, which is pretty amazing. Professor Gates is also a member of the National Academy of Science, the American Academy of Arts and Science, and he's also a member of the American Philosophical Society. So, in this interview, we're also going to be discovering how supersymmetry connects the tiniest quantum particles to Einstein's theory of relativity. So without further ado, let's dive into this groundbreaking interview into physics, math, and science. Professor Jim Gates. So let's get busy.
If nature is supersymmetric, there are all these other particles to balance. I study the mathematics of these things. That's supersymmetry. I do not believe that we are in a matrix computer simulation. And so I have long suspected that there's something like evolution has put these error correcting codes in the places that I have found them, along with Michael and a few mathematicians, in our equations. And so what's really interesting about supergravity is that it uses the mathematics of Einstein's general theory of relativity, but it goes beyond that mathematics and includes aspects of relativistic quantum field theory.
So here guys, we have the man himself, Professor Gates. Welcome to the show.
Well, thank you very much for the invitation.
Well, thank you. And so we're just going to be starting off with a few questions to get to know you better, and then we're going to be going more into questions in your field and what you do every day. So first of all, what inspired you to do what you do?
I was 4 years old. I lived in Canada at the time. And my mother took me to see a science fiction movie. And the name of the movie is Space Waves. It's a very bad science fiction movie. But when I was 4, I think this was the first movie I ever saw. And I heard the word science, and I connected it with adventure and fun. And I decided that's what I wanted to do with my life.
Mm-hmm. Okay, that works. And so what do you even do, Mr. Gates?
Well, my wife has an answer that she often gives people when they ask her that question. What does your husband do? And she says, he makes up mathematics for a living. But since he makes it up, no one can tell him it's wrong. And that's kind of a joke, but it has an element of truth to it. I actually do create new mathematics in an effort to understand things about nature that no one's ever understood before.
All right. So now that we know more about you, let's go into more deeper questions into your field, which is supersymmetry and string theory. So, Professor Gates, what is supersymmetry in the first place, and supergravity? Okay, so let me start with supersymmetry, but we're going to start on the screen. You can perhaps see Mendeleev's table of elements, but this is the form of the table when he first invented it. These days, it looks much more advanced than that. It looks like this if you walk into a classroom. So now I can explain to you what supersymmetry is. If you look at our universe at very small scales, you find smaller particles, first atoms, and then nuclei. And so if you ask yourself, what are the particles that we know about? This is a collection of those particles. In the lower quadrant, you have the electron, denoted by the symbol E. But there are lots of particles that are very similar to the electron. We call them leptons. Inside of protons are quarks. So here are the up and down quarks represented. So these are what we call matter particles. They're the stuff of the universe. In this upper quadrant here, we have the photon, the particle of light. And so I ask people, I've created this chart to ask a question. I ask people, does this look balanced to you? So that's my question to you, sir. Does this look balanced? In what point? In the matter or in the boson? Or all?
Let's just start in the boson part, just the boson part. Does that look balanced to you?
Does not look equal. Does not look balanced.
Okay. So you'll notice there's one box around H, and the H stands for the famous Higgs boson. How many more boxes would I have to put in that quadrant to make it balanced?
You would have to put like 4, I suppose.
Three.
3. Okay.
But there's one already there. And so to balance it, you have to balance this, you have to balance this, and you have to put 3 more boxes.
Okay.
So now we've balanced this sector. Let's imagine we've done that balance. What would we have to put over here to balance this and what we balanced here already? Well, how many more boxes here?
8.
8. And then we would see balance on both sides of this. And
Yes.
now if we want to balance the bottom, you can see we have to put a lot of more boxes, and it looks like that. This is supersymmetry, where you have this balance between these are the particles that we know that have been discovered at colliders, like the Large Hadron Collider. If nature is supersymmetric, there are all these other particles to balance. And I study the mathematics of these things. That's supersymmetry.
All right. And so, what inspired you to get into this?
So when I was in graduate school, and this is from 1973 to 1977, the mathematics for these kinds of ideas was completely new. And so I was excited to learn new mathematics, but more importantly, if this is an accurate picture of nature, it means there are more forms of matter and energy than we had ever thought about before these ideas were introduced. And that just excited me to be on the ground floor of a new scientific discovery.
Okay, so you're saying that with supersymmetry, it shows us that there are even newer and other types of matter. Interesting. Okay.
And energy, yes. That's what we know is in this chart, right? So the particles down here are matter, electrons, quarks. These are various forms of energy. This is what we discovered. But if this mathematics is correct, in the future we'll discover more.
Okay. Okay. And so, what is supergravity?
And so here's another one of those kinds of charts. Now, this isn't quite our universe. Maybe you heard the word quantum. People talk about quantum physics. So in 1995, a scientist named Edward Witten and these two physicists who are English, Chris Hall and Paul Townsend, suggested that they know how to combine the idea of the quantum with gravity. And that construction is what's shown in this picture. You can see the left-right. It doesn't quite look like it's left-right balance because this is a picture not of quite of our universe, but a universe that has 10 directions, which is what this quantum gravity theory seems to need. So that's the balance, can even be done with gravity. So we call that balance supergravity. Here we have our chart where the electron is represented by these two symbols here. If the mathematics of supersymmetry is correct, these two parts of the electron, this stands for spin up and spin down, have to have superpartners. The superpartners are over here, and as you can see, they're roughly speaking in the same location in the square. So that's the basic idea of supersymmetry, namely that when we look at the standard model, which looks like this, you only have the electron. You don't have the superpartners. But if the math is correct, the superpartners will be discovered at some point in the future. And it's not just for electrons, it applies to all the particles. Let's go back to the standard model again. Here in the standard model is a representation of the photon, the particle of light. Now, this is what we know from experiments and observation, but if this mathematics is correct, then the photon, which we have represented here, has to have a superpartner, and that superpartner is over here. So the basic idea is standard model looks like this. Supersymmetric extension of the standard model looks like this. So does that clear up the notion of what is a superpartner?
Yes, it sure does. I see.
Wonderful. Now, the other thing about you could ask about these superpartners is what's different about them. So let's go back to the photon. So the photon is the particle of light. It allows us to see. The mathematics says that if supersymmetry is correct, it has this superpartner. Now, the photon also does more than let us see. It is what conveys the electrical repulsion between two charged particles. Maybe you know that like charges
Yeah.
repel. Well, that's because they're exchanging photons. So this thing is what we call a force carrier, and that's why we also call it energy, because it has that energy to make that exchange. The superpartner will also be a force carrier. So what's the difference between these two? It's that their rates of spin. You see, the photon, which is here, and both of these should be regarded perhaps as little balls spinning on their axis. The photon spins at twice the rate of the photino. So that's the difference between these objects. Now let's look at the electron with its spin up and down, spin down components, and ask what's the difference between the electron and their superpartners, which are called selectrons. By the way, let's do this naming thing too. Anything that we name over here, we simply put an S in front of its name over here. So here's the up quark,
Subquark.
is the up squark.
Oh, upsquark. Okay.
This is the down quark. This is the down squark. And so as we go across the bottom, you take the standard name and you just put an S in front of it. That's more time. This is a particle called the muon, which is kind of a heavy version of the electron. So if I move to its superpartner,
Musquark.
no sir, muon,
Muon.
this is a smuon.
Oh, okay.
So whatever name you have over here, you just put an S in front of it. Let's do it one more time. This is called the tau particle. When we move to its superpartner, what do you think its superpartner is
Stow.
called?
Stow.
Tau. Bingo. And one more time, all three of these objects are called neutrinos. So what do you call all three of these objects?
Subtrinos.
Neutrinos.
Oh,
You put that F.
Okay, okay.
Okay, so that's how this game gets played about supersymmetric names. If you on the bottom part, you take the name of the standard model particle, you put an S in front of it, and then you pronounce it. Now let's play that same game with the energy.
Yes.
This is the photon, and so the rules change above. And you take the name, you put I and O after it. So this is the photon, this is the photino.
Fotino.
So if we call this thing the Z, what would we
Z.
call
Z. Sorry, what was it again? E-I-E-N-O?
this? Yes, so how would
Okay.
you pronounce
Well, Zino?
Zeno?
Oh, Zeno, okay. Zeno.
Particle, there are actually two here. We call them the W particles. So what would you call their super partners?
The Wino?
Yes, sir. So that's how the game gets played. On the upper part, you put I and O after the name. On the lower part, you put the S in front of the name. So here is the famous Higgs boson that was discovered at the collider in Switzerland. What do you think we would call the name of its super partner?
The Hino?
Higgsino.
Oh, sorry. Higgsino. Okay. Yeah.
Now, again, what's different between these things? Well, the Higgs boson and all of these objects don't spin at all. They're at rest. Whereas their superpartners all spin. So as you move across this vertical line, what's changing is the spin of the object. If we look at the electron and the quarks, they spin, but their superpartners, namely the leptons, all of these things are called leptons, and the squarks, because all of these things are called squarks, do not spin. So that's the basic rule for how supersymmetry gets played.
And so, how would this be important in physics, and how could this be interesting? How could this
So
change?
let me tell you a little bit of physics history.
Great.
No one watching your video is going to be surprised to hear the word electron. So there
Yeah.
was a time when no human had ever thought about an electron. The first person to do this is a man named George John Stone. He thought of this idea, and yet no one had ever seen it. So why is it important that he had this idea? Because all of the electronics around you comes from that idea. So these new
Yeah.
particles that we're talking about, the super partners, the expectation is that if they're there, if the math is right, then at some point in the future, there's going to be some kind of technology that will be super technology, unlike anything we've ever seen.
So like you said, the electron back in the day was considered as this new thing, this what we believe to be just as like in a way equivalent to supersymmetry, which is also something that we just saw traces of, and that we would think that if we ever discover what the uh, the symmetrical version of the electron is, might be this new revolutionary discovery or something. So we still don't know what it is.
Well, we still haven't even discovered it. Remember, I keep emphasizing it's math right now. I mean, people like me see things in mathematics, and we can see these objects in the mathematics. If we discover it, then yes, there's probably some. Look, it'll take over 100 years. That's what you have to understand. People always ask, "Well, what's that good for?" That's not the way science works. The electron was thought about in the 1800s. We didn't get electronics until the middle 60s, 1960. That's 160 years. And so it's going to be like that for this stuff. We will never live to see the technology that comes from these things.
Sad, but we hope that it's gonna be this new thing that's
And
nice.
hopefully useful for humanity.
And so since you also do string theory, could you also explain to us what that is basically? We hear it everywhere.
Lord, yes, a lot of people talk about string theory. So when we think about atoms, the most convenient picture to hold in one's mind is that it's a very tiny ball. Okay? So imagine you have a ball, and how small is that ball? Well, that's what we can talk about doing what we physicists call powers of 10. Start with a meter stick, cut it into 10 equal pieces, throw away 9, and you go from something this big to about something that big. Now, take that remaining object, cut 10 equal pieces out of it, throw away 9, and you get something about as wide as my fingernail. So if you want to get to the size of the atom, you do this process 8 more times, and that tells you how big the atom is. So you have to think of a ball that small, okay?
Okay.
Now, uh, you can ask, is there anything smaller than the atom? And the answer turns out to be the nucleus of the
Yes.
atom. How many times more does it take for us to get from the size of the atom to the nucleus? The answer
How much?
is you do that process 5 more times. And now you can ask the question again. Is there anything smaller than the nucleus? Now
Yes.
we have no technology for trying to observe that, but we do have mathematics because mathematics is the way that we can explore the universe before our technology lets us measure things.
Mm.
There is some evidence that starts in the 1970s that if you carry that same process out that I described for you, 35 or 36 times, you will find these things that are sort of like little pieces of spaghetti. They're like filaments. They're like strings, and that's why we call them strings. Their mathematics is very similar to the mathematics of violin strings, and that's how they got their name.
All right. And so, from what I learned is that the small strings move at a certain frequency, which then later make up our objects, eventually.
Well, they if they vibrate at certain frequencies, if we look at the mathematics, they behave like particles that we know. And
Mm.
so different vibrations give you different particles.
Well, interesting. Okay. And so, one last question about what you do. is
What are error correcting codes?
because you seem to have a lot of theories on that, and you also believe that, well, we might be even in a matrix inside of a computer by seeing how error correcting codes are also in the same equations as other equations. So please explain to us.
Yes. Well, first of all, I do not believe that we are in a matrix computer simulation. This is a statement that many people have attributed to my research, but if I believe that, I would not be a scientist. You see, if that's a true statement, there's no way to disprove it. And one of the things that most people never get to is science is only about the things we can disprove. So if you make a statement that we're in the matrix, there's no way to disprove it. It's not science. So I don't believe that for a while at all. I know there are tons of videos online and all that stuff, but that's all fake news. That's misinformation. I've never said that. I've never believed that. Okay? Let's start
Okay.
there. Now I'm going to show you, I'm going to show you images of the mathematics that I first started in 2004. And then working with other people, we discovered there were computer codes in the pieces of mathematics that I and another gentleman by the name of Michael Fox invented to describe the superpartners. That's why we create. Okay. So let me show you a picture. Okay, so when you, in 2004, working with another scientist named Michael Fox, we were studying the mathematics of that balanced picture that I showed you, that supersymmetry.
Yeah.
What we found is it's a little bit like, I don't know if you've taken biology, but when you want to look at microscopic things, you have to have a microscope.
Yeah.
Right? Mm-hmm. So we took the mathematical equivalent of a microscope and looked at the equations that had that balance. And when we looked deeply in them, we found objects like this that are kind of like they're pieces of math, but they're kind of like the DNA of the equations we were looking at. Okay?
Okay.
And it turns out we studied them and we found out that they can do the following. They're not rigid. They move. And in fact, there are mathematical operations that correspond to what you're seeing here. They're called matrix multiplication. At some point in your study of mathematics, you'll learn about these objects. And then we're doing calculus here, it turns out, because what calculus does on these tiny mathematical genes, we can call them, we gave them a special name, we call them adinkras, is that when you change height, you're doing calculus. And now you can see there are two identical objects, one on the left and one on the right. And so you might wonder, could I get perfect matching? And maybe it's an object and its mirror image. So we can perform some motions that you can see in this movie. And we can then use this to show that, yes, these two things can be perfectly matched, but they're matched in such a way that the lengths even match. And there we go. Now let's open this back up. So it looks like this. Let me stop the movie here.
Well.
And the final image looks like this. And what we found is in order to get this final image, you must have these error correcting codes in there. And this is how we uncovered it. It's a stunning result that is really hard to believe unless you actually have done it.
So you had to try an error correction code, and you were trying multiple, and then you found the coincidence that it was.
Yes. So let me go through this again. When we do the balance, it's a bunch of equations. I'm actually showing you the equations right on the screen now. In 2004, working with another physicist named Michael Fox, we took the mathematical equivalent of a microscope and looked at these equations. When we did that, we found these things. We call them adinkras. It's just a name that comes from West Africa. And the way to think about it is that these are the mathematical genes of the equations I'm showing you on this page. Now you'll notice these genes are at two heights. It turns out it's this property of two heights that contains the information about the error correcting codes. What we did is we studied the folding up process that I showed you in the movie. There's only one way to fold, and that fold uses error correcting codes, strings of ones and zeros, and it uses them in a very special way that humans have known about in computer science for about almost a century now. So error correcting codes in the laws of physics. No one's ever seen it before.
And so what do you think that this means? Now that you saw this, what do you exactly think that it means? Because you have clearly stated that you don't think that that we're in a simulation. So
Right.
what do you think?
So this is a question that for several years I pondered. And so now let me take you back to biology. If you consider actual living creatures, they have DNA inside of them.
Right.
And that DNA, as you create a new cell, that DNA has to make a copy of itself.
Mm.
Now, if that copy is not perfect, then you start with a DNA double helix, and it copies itself. If the copy is not perfect, then the creature that possesses that imperfect copy is a mutation. That's the meaning of the word mutation. Most mutations are not capable of sustaining life. They would die. Only a small subclass of all possible mutations are viable. And so biologists and geneticists for decades have said, how could these DNA strands reproduce to reduce the number of mutations? And the answer turns out to be error correcting codes. So the only other place that error correcting codes are known in nature, not in the work that humans do, but in nature, is in genetics. And so I have long suspected that there's something like evolution has put these error correcting codes in the places that I have found them, along with Michael and a few mathematicians in our equations.
Einstein's relativity explains in large scale, like planets and black holes, while quantum physics explains these tiny particles like quarks and electrons. How does supergravity bridge these two concepts into one unified theory?
Well, thank you for the question. First of all, it is not a completely successful merger of the two, but it's a progress that advances over anything previously. So how does it do it? Well, the theory of supergravity was first uncovered in around 1975 by two different groups. And what's unusual about the theory is A, it was not discovered by people who traditionally had been working on Einstein's theory of general relativity, astrophysicists and cosmologists. Instead, it was discovered by people who work on particle physics, that is, the physics of quarks and tiny objects. And so, what's really interesting about supergravity is that A, it uses the mathematics of Einstein's general theory of relativity, but it goes beyond that mathematics and includes aspects of quantum field theory, relativistic quantum field theory. Now, the reason that's important is because if you have a complete view of the universe, you shouldn't have two different theories. I like back
Yeah.
many years ago, I said if you have a theory of everything, then it can't be the case that you say I have a theory of everything in part A and a theory of everything in part B. Part A and B have to be connected to each other.
Exactly, that's what I say. I agree completely, yeah.
Good for you, and that's the thing that supergravity does. Now, the way it does it is by including this principle called supersymmetry, which we've talked about as a balance
Yeah.
when we look at the standard model. And so let me give you a story about quantum mechanics that I recently told an audience in London. Suppose I had a boiling pot of water. And no, let me first of all just take a pot, don't turn the heat on, and let it become still, and then put a toy boat on the surface, and then give it a flick with my finger. What do you think will happen with the boat if I do that?
I think that it's slowly gonna float at a speed, and then it's gonna slowly go slow.
Correct. So it will start moving on the surface of the liquid, and because of friction, it slows down. Suppose there was no friction, what would happen?
Well, it would just go on and bounce on the corners infinitely.
In other words, you have just uncovered Newton's law. F is equal, I mean, that an object in
Yeah.
motion will continue in that motion, right? That's what you just
Yeah.
described. So Newton's law, we can see in this toy example. Now, suppose I turn the fire on under this pot that the liquid is in. What happens to the surface of the liquid?
It starts bubbling and it
It
starts
starts bubbling. And
rising.
now, right, so now let me once again take my toy boat, put it in the liquid, and give it a flick with my finger. How does it move now?
Well, that's kind of like chaotic. It's kind of random.
Right, exactly.
Yeah.
It's chaos. This is wonderful. This is wonderful. This is exactly the point about quantum mechanics. You see, quantum mechanics acts as if the universe, even if you remove everything from it, is like a bubbling surface. And when
Wow.
you try to and when you try to make small particles move through it, they encounter those bubbles, and that's why it becomes chaotic and non-Newtonian. And so
Wow.
supergravity was constructed to include this, and that's how the bridging goes.
So supergravity then helps us understand this better, and it's basically the concept that you just showed, but in space.
Yes,
Okay.
it's this concept, by the way, of the bubbling surface has a name. It's called the quantum vacuum. And so
Yeah.
we believe that because of laws of relativity and because of the laws of quantum mechanics, that even if you take an empty chunk of space, particles pop in and particles and antiparticles pop in and out of existence. They're just like a boiling surface. So when you try to take out an electron and move it through there, it encounters these particles, these virtual particles, as we call it.
Amazing.
And so that's the best way I know how to understand quantum mechanics.
All right. And so, how does your research help us understand mysteries like dark matter or like the Big Bang?
So my research doesn't directly touch on either of those two things because what I'm doing mostly these days is mathematics. What I'm trying to make sure in my research is that we have the mathematical foundation to be able to respond to the question that you had just asked me. And in particular, we want to be able to respond in a way that is consistent with quantum theory, not Newtonian gravity. In other words, it's got to be consistent with the boiling pot, not the still pot.
All right. Okay. Well, amazing. And our final question before we wrap up: what is your message to people watching, whether it's kids or adults, who are aspiring to get into physics and who want to, well, pursue a career in physics?
Well, you've asked actually several questions, so let me try to break them apart. If the desire is to actually pursue the kind of physics that I do, then what you have to do is to learn as much and as deep the content about both mathematics and physics that you can at the stage where you find yourself. So, for example, I was 4 years old when I decided I wanted to become a scientist. I was 16 when a teacher taught me it was not all of science I wanted to do, but only physics. So, from that point on, I concentrated on learning physics. And the thing is that you have to learn the physics that people did hundreds of years ago. Otherwise, you don't have a deep understanding.
Yeah. So as physics is gonna progress in time, it's gonna basically be at a point where it's a little bit impossible to make these small steps in the research because you have to go.
Yes.
Yeah.
And it's a little bit like learning to play a musical instrument. I don't know if you play a musical
No,
instrument,
I don't.
Etan, but if you did, the first thing your music teacher would do is make you learn the scales. I took piano lessons when I was young, so I remember hours of my fingers da 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 da
Yeah.
da da da, and it seems so boring and useless. But unless you do that, you can't learn to play the piano. And so, in the same
Yeah.
sort of way, the boring and useless mathematics that people often talk about in school, if you want to do physics, it's like learning to play the scales. So that's what you have to do if you really want to become a physicist.
Mm.
On the other hand, if you just want to understand what physicists do,
Yeah.
and after all, most that's what most people want to do. They want to get a sense of what's going on. Then the things that I advise people is A, be a skeptic. Now, what does that mean? Well, you see, Einstein once said that it is the outcome of most physics theories to be proven wrong shortly after they are presented. And for those small number that for which
Yeah.
they avoid this fate, nature only says maybe. So this is one of the things that people often mistake about science, that scientists is giving you ironclad statements. That's not what science does. What science does is give you the best observed and best mathematically formulated statements about nature. And because we're not infinitely smart, it means that as we observe more of nature, we're going to change what we say. So you need to have this sophisticated understanding of the evolution of field, that it's not giving you truths, which is what people often think. What it is giving you is humanity's best possible explanation at the time you ask your question.
Amazing. And what is a general message that you want to give to people who maybe don't want to pursue a career in physics, but who are just interested? What is a general thing that you would say to people like that?
Well, I think partly what I've just said covers that. But the other thing that I would say is don't abandon the foundation that science has given Western civilization, especially in the last 500 years, and even longer for other civilizations, like the
Yeah.
Chinese civilization goes back around 5,000 years, and then the Middle East, I'm sorry, the subcontinent civilization, similar time scale. So don't abandon what we have learned from science. And so what we've learned from science? Well, we've learned that if you want to talk about nature, you have to talk to nature. And the way that you do
Yeah.
that is by performing observations and performing experiments. That's step number one, is that humans are not capable of just thinking of the answers.
Of course.
We have to be in conversation with nature. Step number two is that the way that science works, every generation of new scientists is responsible for questioning everything the generation before them told them,
Yeah.
because science recognizes that some of that might be wrong. And then the final thing is be brave. And when a fact is presented that contradicts your beliefs, science tells us we have to go with the facts and observation.
Okay. Well, thank you so much for this amazing interview, Mr. Gates. Thank you so much. And well, yeah, I'm sure that a lot of people who are passionate in this field will really take away from this. So thank you so much.
Okay, well, thank you for the opportunity to speak and the invitation.
Well, thank you so much for you coming here. Thank you.